Good afternoon, everybody. Today we are going to sketch this rational function, and we're looking at a quadratic over another quadratic. And so we're going to look at some funkiness, let's say, that's going to go on around the horizontal asymptote. Okay, so first of all, we can get our vertical asymptote, right? Our vertical asymptotes always come from the values of x that makes the denominator be 0, right? That's pretty straightforward to find, right? If x squared is equal to 0, right, then that leaves us with only a vertical asymptote at x is equal to 0. And so our y-axis is going to serve as a vertical asymptote, okay? Now, our horizontal asymptotes, right, those horizontal asymptotes are really the end behaviors of our function as the x values go out to positive infinity or to negative infinity, right? And so in the language of calculus, what they really come from is the limit as x goes to positive or really negative infinity of our function, right? Of namely x squared minus 4x plus 3 all over x squared, right? And then to be proper, since we're going to go through this, might as well go through this properly, we could write this as the limit as x goes to positive or negative infinity. We're going to get the same result either way. Let's divide each term of the numerator by x squared. And so we'll have x squared over x squared, which is 1 minus 4x over x squared. You can imagine the x is going to cancel out one of the x's in the denominator. And so that second term, the minus 4x over x squared, is going to simplify to minus 4 over x, right, with one factor of x canceled out from both the numerator and the denominator. And last, we'll have the plus 3 over the entire denominator of x squared, right? And of course, we're taking the limit of this entire expression. And now, without too much cognitive effort, you can tell that the limit as x goes to positive or negative infinity, that just means as the x values get incredibly large, right? As x gets incredibly large, 4 over x is basically 0, right? It's going to approach 0. And so will the third term, the 3 over x squared, even faster, because as x goes to infinity, x squared gets to infinity faster, if you want to think of it that way. And so this term is going to go to 0. This term is going to go to 0. And so all we're going to have left is a value of 1. The limit as the x values get really, really big, that is the end behaviors of our functions, of our function rather, far to the right, far to the left, is going to be a y value of 1, right? Because after all, our expression here is our function for y, right? And so that means that we get a horizontal asymptote at y is equal to 1. Now that we've laid it out using limits, from here on out, you can use the idea that if your numerator and your denominator have the same degree, that is the highest exponent on any term with a variable, i.e. here, they both have degree 2, right? If both the numerator and denominator have the same degree, then the horizontal asymptote is simply the ratio of their leading coefficients. For us here, that's 1x squared over 1x squared. And so the ratio of the leading coefficients, the coefficient of the term with the highest power, is going to be 1 over 1, which is 1. So this is our horizontal asymptote. Y equals 1. Okay? Now, we can start sketching our curve a little bit. So the numerator, you'll notice, is a factorable quadratic, right? And so that means that we can write y as x minus 3 times x minus 1. I'm guessing some of you were waiting to factor that. All over x squared, right? Now, that means that that numerator can get us the x-intercepts, right? Because if the numerator is 0, 0 over anything, as long as x isn't 0 itself, right? That's a non-permissible value. But 0 over anything is 0. right? And so that means that we're going to have two x-intercepts. We're going to have x-intercept at 3 and at 1, right? Because again, 0 times anything over 0. Sorry, 0 times anything over anything, rather, 0, right? So that means that at 1 and 3, we have an x-intercept, okay? Now, we can get other points pretty quickly without too much effort. We can get our y-intercept, if it were possible, but now we have a vertical asymptote at x equals 0, so that's not going to be possible. So there's no y-intercept here. We have a vertical asymptote at x is equal to 0. And so now we can sketch some points. There's not too many points that are actually really quickly available. So let's plug in some values. Let's plug in -1. We know we have a vertical asymptote here, so it would be nice to have some points on either side of that vertical asymptote, right? So let's find some when x is -1. Y is going to be, that's going to be -1 squared minus 4 times -1 plus 3 all over -1 squared. And so that's what? That's 1 plus 4 plus 3 all over 1. And so that's 8, right? So when x is -1, y is up here at 8, okay? When x is -2, y is going to be -2 squared minus 4 times -2 plus 3 all over -2 squared. That's going to be 4 plus 8 plus 3 all over 4. Y is 15 over 4, which is 3.75, right? And so it's going down. At -2, we're around 3.75, we're around here, right? And this is going to look a lot like the boomerangs in 1 over x squared, right? And so we're going to have something like this. And it's going to spike upwards again, going right up against the vertical asymptote. The right-hand side is what I really wanted to pay attention to. Now, this right-hand side is going to have some strange behavior. Let's plug in some values. When x is 1, we have an x-intercept. When x is 3, we have an x-intercept, right? Where are we going to be in when x is 2? Let's say. When x is 2, y is going to be 2 squared minus 4 times 2 plus 3 all over 2 squared. That means that y is 4 minus 8 plus 3 all over 4. And that is -1 over 4, -0.25. And so that means that here we have a point down there below that x-axis. And now if you're at all familiar with 1 over x squared functions, you know that this isn't really the behavior you're going to expect, right? Now, even more than that, if we plug in an x value between the vertical asymptote at 0 and that x-intercept, that initial x-intercept at 1, let's say 0.5, I want you to see what happens. If x is 0.5, let's compute the y-coordinate. Y is going to be 0.5 squared minus 4 times 0.5 plus 3 all over 0.5 squared, right? And so 0.5 squared, that's 0.25 minus 4 times 0.5, that's 2, right? Minus 2 rather, all over again 0.25. And so y is, that's 1.25 over 0.25, right? And that is equal to 5. When x is 0.5, we get a y-coordinate of 5. That means that we have a point around here. And that is likely not what you expected after seeing this boomerang in the top left corner and these 3 points down here, okay? Now, this is going to ask you the question, how do these points connect, right? We know the horizontal asymptote, that y is equal to 1 line, that serves that asymptote. That's the behavior of our function. This is why I really wanted to get into the limit part of things. That's the behavior of the function as the x goes towards infinity, right? That's certainly going to be the end behavior of our function, but that doesn't really tell us a whole lot about the nitty-gritty details when the x values are really small, right? This tells us a lot about the end behaviors when the x values are gigantically large, not so much for the x values that are really small. And so we have to think our way through over here, right? If there's a point above the horizontal asymptote and then immediately after or shortly thereafter a point below, logic says that it's probably going to have to cross that horizontal asymptote at some point, right? And it turns out that that's okay. You've likely learned that horizontal asymptotes are never crossed, and that's simply not true. They're never crossed as the x values go off to infinity. As the x values get incredibly large, as they approach infinity, the horizontal asymptotes do not become crossed. But for small x values, we can have some strange behaviors happening here in this region of the graph, okay? And what's gonna happen here is this does explode up to positive infinity. As x gets closer and closer to 0, this does spike upwards, like so. But then it crosses here. And then it's going to dip. And then it's going to hover just below that horizontal asymptote as the x values approach infinity. And if you're curious, this intersection point between our curve and our horizontal asymptote, we can, if we'd like to, we can solve and find the coordinates of that point here, okay? Let's call that our crossing point. I don't believe that's a formal term, but let's make up a term for the sake of this example. That crossing point is found by setting our function equal to 1, right? Because that's the equation of the horizontal asymptote. And so let's do that. Let's set 1 equals x squared minus 4x plus 3 all over x squared, right? And it turns out this is not going to be super difficult to solve, right? We're going to start by multiplying both sides by x squared to cancel out our denominator. And so, like so, 1 times x squared, that means x squared is equal to x squared minus 4x plus 3, right? That's not a terrible equation to solve. The x squareds cancel out, and so we get 0 is equal to negative 4x plus 3, and that means that x is equal to 3 over 4, or in decimal form, 0.75. That should make sense, because here we have a point when x was 0.5, right? And we had an x-intercept when x was 1, right? 1, 2, 3. And so this point of intersection between the horizontal asymptote and our function itself should be between 0.5 and 1, right? And so that is the point where we cross that horizontal asymptote. That does happen from time to time. It's something we have to check if we suspect that it might be happening in our sketch. And in any case, the rest of the behavior is more along the lines of what you've seen in past examples, I'm guessing. But we do cross that horizontal asymptote, even cross the x-axis, and then we trail off just below our horizontal asymptote at y is equal to 1 as the x values approach infinity. So we approach infinity under the horizontal asymptote, and we approach in the x values negative infinity, hovering above that horizontal asymptote. Again, the horizontal asymptote identifies the end behaviors of the function. It doesn't tell us if we're going to go above or below. It just tells us that we're going to approach that horizontal asymptote as x approaches infinity. So I hope that helps. This covered a lot of concepts. I really hope this helped piece some things together for you guys. And thanks for watching.